Right, okay, so this is the continuation lecture on D2A, carrying on from where we left off at the end of last term. And this will just cover the main points of how to do digital to analog. And there are several ways. None of it's particularly complicated, I don't think. But sampling a voltage is the simplest approach, where you just take a string of resistors, put a reference voltage at one end, and then switch in with these switches these levels as you need it to give you a summed voltage here, which is then added at the output there. So we take a tap off of a resistor chain. So we've got a 3-bit DAC shown, and we just have to set the switches, the B1, B2, B3 accordingly to allow the sampled voltage that we're interested in to arrive at this point here. It's very straightforward. There's a summation of voltage method which makes use of the virtual ground of the op-amp and is just really a giant adding circuit. And there are various different implementations of this kind of idea. Again, we can just put in our digital levels at this point here, and we weight them accordingly to give them different priority. They're added at the virtual ground junction, and the current flowing through this resistor then allows us to generate a voltage that is proportional to the weighted inputs. And you can see that they're binary weighted in this case, and the more of these you'd have, the more resistances you have to have. So it says the attraction of this is that the input voltages can be digital signals, so these are the inputs here, but they have to be the same amplitude, which is great if they're digital signals because they're all coming from a logic system, so they will be the same amplitude. And then we have to weight the values of the resistors accordingly to give us the right weighting. As you add more and more resistors to this, we then have to be more and more accurate in terms of the values of those resistances to keep the overall error down. There's a nice system called an R2R ladder. This sort of offers an alternative because here only two different values of resistance are required, and these are values of R and 2R. And this makes use of some of the analog theory that you've done either in previous modules. I think we talked about this in the first year course, if you remember back that far. And again, it makes use of some quite neat circuit theory, because we've got a ladder network here, and there's various simplification rules that can be applied to ladder networks in terms of circuit analysis. And in fact, this is a very good use of such techniques. So a bit of revision of the ladder network, so I'm not going to spend too much time on this because this is sort of first year stuff, and then maybe even Alex goes through it as well, because it's a nice thing academically to look at. So if we make a ladder network with impedances in these type of ratios, we've got 2 and 1, 2 and 1, 2 and 1. We've made that's called a ladder because these are repeating sections, and it looks a bit like a ladder on its side. And so we've got repeating section, repeating section, repeating section, and then we've got a practical source attached onto this end here with an internal impedance of 1 ohm, which happens to be the same as this here, and a voltage of, in this case, 10 volts rather. And so we can actually take the first part of this system here and we can simplify it via the Thevenin theorem, because we can now see we've actually got, if we combine these, we've got a 2 ohm resistor, 1 plus 1 is 2, and then we've got in series with another 2 ohm resistor. But if we suppress this source, we can see that we've actually got a 2 ohm resistor in parallel with another 2 ohm resistor. So the Thevenin equivalent of this is actually equal to the open source voltage, which if you look in here you will see that it's because it's this equal potential divider. If there's 10 volts here, you will see 5 volts here, so that's your 5 volt source. And you will also see an equivalent impedance looking into here if you suppress this of 2 ohms in parallel with 2 ohms, which is 1 ohm. And that's quite an interesting response because that bit there, which is the first part of this system here, actually sort of replaces this, so we can plug that on here, and then we can do the same thing again, and it becomes a sort of a cascading system. Spelling mistake there. And the only thing that's actually happened is that the value of this source has changed. The value of the impedance has remained constant. And each stage reduces the Thevenin voltage by a factor of 2, and the output impedance is not affected by changing the input voltage, which is an important feature of this. Only its eventual magnitude when it gets to the output. In other words, the output voltage is V out is V in over 2 to the n. So we can apply a voltage at any equivalent part of this resistor change, and it will appear at the output reduced by the number of stages it started away from the output. So and we do that by superposition. So it gives us the result that V out then becomes a combination of V1 over 16, V2 over 8, V over 4, V3 over 4, and V4 over 2, where the input voltages are coming from these digital levels here. So we're either setting them to be V in, or we're setting them to be 0. And so when we can set these to 0, you can see that becomes a 0 if V1 is a 0. And binary righted. So whatever word you present here just manifests itself as an output voltage here in terms of the various ratios. Purely because these resistances have this ratio, and so you can get more and more bits of this by adding more and more of this ladder stage to it, but you haven't got to worry about the accuracy, particularly of the resistances, because they're the same value as each other. As long as you can trim them to be the same as each other, we're not starting to deal with stupidly small values or stupidly high values. So that's quite a nice solution. And if you want the example of this in some detail, this is an example of how to do it. Is it worth going through this? Well, a little bit, I suppose. It just shows what's going on. So it's really just doing Thevenin equivalents for different voltages, so and a superposition. So we're adding in a voltage here. We're doing a Thevenin equivalent of what that actually looks like from here and plugging it on. And if you follow this through, you can see exactly how these output voltages start to improve. How they become weighted in the right values. And you can see now we've been doing the same thing by putting a source in here, looking at what's happening in this area, giving the Thevenin equivalent of this resistance chain, which is easy to do because we just add those two together. They're in parallel with that. That's 2R in parallel with 2R, which becomes an R. R in series with R becomes a 2R resistance again. And so the whole thing just cascades itself down the pipeline. The best thing for you to do is to try and follow this through. I've put all the red and the green lines on, and a bit of scribbling at the side of this, and you'll get to the answer quite easily. And that brings you back to the original solution, which allows that to happen. So V1 to V4 can be digital inputs, and they're coming in from here, of the same magnitude V, which can be just the logic level, 5 volts, 3 volts, whatever it is. And you can change this as much as you want. And in fact, this is such a useful technique. You can buy pre-packaged packs of resistors for just such application. And here is an example. Bourne's R2R series thick film networks. You can just buy effectively a chip that's only got resistors in it, but they're very well matched. And they're also on the same substrate, which means that as temperature changes, they'll all change with the same temperature. So this, using these, it's quite easy to make an A to D converter from individual parts. It says here, when I last looked, it was £1.07p from Farnell for a bunch of matched resistors. If you want to go faster, you can actually switch currents rather than voltages, but the R2R structure is still used. So if you want to look up current steering converters, feel free. Multiplying digital to analog converters is another way of doing it. We looked at the multiplying DAC a little bit earlier in the course. Multiplying DAC takes a reference voltage, can be AC or DC, and scales it by a digital world. So it's usually sort of used for, say, setting volume controls, that kind of stuff. But in this case here, you can digitize signals quite nicely by putting it the wrong way around in many ways. If you set the digital word as 128, you'll get a value of half V in as the output. So if you make V in an AC signal, you can just attenuate this. So this is how you make the volume knob. But by just changing the amplification factor, if you like, within this device, you can make Vref, a voltage come out of here, whatever. So you're changing the code word in here, and that changes the multiplication factor on the reference voltage coming in, so you can then start to get an analog signal out. Alternative techniques. So the main interesting alternative technique to this is pulse width modulation, which we looked at earlier, and we can use PWM to actually generate analog signals. And we just have to remember that the duty cycle of the pulse width modulated signal is related to the average value of the PWM. And if we low pass filtered the pulse width modulated digital signal, we get the average as an output, and that is our analog signal. So most microcontrollers have got pulse width modulators built in, so you can actually generate pulse width modulation as an output. If you just put that through an RC filter, you can get in some cases quite a good D to A converter, and in other cases, if you're not careful, quite a bad one. It just depends what you want to do. But the details of this, of why it's a bad one, is again Nyquist comes into the problem, and we're going to need 2 samples at least of the highest frequency to be able to construct our signal again. This means that we're going to be immediately limited to the frequency of the pulse width modulation signal, the frequency effectively of the switching frequency over 2 as our base bandwidth B. There is also a constraint, and it's not an obvious constraint this, that the magnitude that you can get out is limited to 2/pi of the amplitude of the PWM signal. So whatever 2 of pi is 0.6, I think. If your amplitude of the PWM signal is 0 to 1 volt, then the maximum amplitude you can get out is 0.6 of a volt. There's an interesting paper here which tries to explain it. If you're interested, you can go and look that up. So in crude frequency terms, and the reason it's crude we'll talk about in a minute, is we can in principle therefore output baseband signals at up to half the PWM carrier frequency. But note that many, particularly internet authors, claim that you can output signal at up to the PWM frequency. But this isn't true, not without a lot of distortion anyway. There are some other issues with this. You've still got to filter your output signal because it's still digital at that point, and then you need to have potentially a very good filter to chop off other stuff, and there's a reason for this as well. As you can probably gather, there's some suspicious looking red arrows on this graph here. The problem becomes that there is a spectrum associated with the PWM signal rather than it being just a single frequency, because it's in its simplest case it's a square wave. Yeah, if you've got 50% pulse width modulation, you end up with a square wave, a 50% duty cycle, and the frequency response of a square wave has lots of harmonics in it as well. It's a Gibbs function. You can go and analyze that, or Fourier transform or whatever. So this itself has going in the frequency domain is going to have lots of frequency spikes of it, and once it's modulated onto the a carrier, so in fact, yes, you end up with double-sided frequency spectrum, and you can start to see that what you're going to end up with are harmonics of the switching frequency spreading in to your band of interest if you're not careful, and the amplitude of these signals is dependent on the duty cycle of the PWM as well. So if you've got a wide PWM cycle, these spikes are less high, but if you've got a big duty cycle, 50%, then this is its maximum, and these are accordingly large in comparison as well. and they will, in principle, spread infinitely down here. So if you're not careful, and if you change this really fast, you end up with these being generated, because effectively what you've got, as you're changing this duty cycle backwards and forwards with the modulation that you're putting in, you can do an analysis of that. It's not easy to do that analysis, but effectively what you've got is a phase modulation signal rather than the frequency modulation signal, and that will itself generate a whole load of extra sidebands as well. So you have to be careful that these sidebands do not spread into your band of interest, because once they're in there you can't get rid of them. So this usually means that in terms of your frequency of your PWM, if you want a good system, you're limited to a band of interest of about 10% to be safe of the PWM frequency. So oversampling is the order of the day here, if you want to get a good output. It's used a lot in switching converters, because actually linearity is not necessarily, strictly speaking, required in those kind of systems. But if you want to use it for should we say proper D2A, you need to make sure that your switching frequency is very, very high compared with your band of interest. Then it works quite nicely. But there's no easy way of working out exactly what the bandwidth has to be. And this is then repeating what I've just said. Teaches me. Go to the latest pointer. So we're going to need to low pass the PWM to get our signal, because that's our bandwidth of interest there, and it says it's wise to make the bandwidth a small fraction of the PWM to avoid errors being introduced from the phase modulation sidebands, these spikes here spreading down into this band here. So if we make this really narrow, the chances of these appearing are low. And I say it's a good way of making a quick and dirty DAC system, or even a quick and good DAC system if you can match some of these requirements, because PWM systems are available in most microcontrollers, and at low frequency it's pretty good. Not so good at high frequencies, because sine x over x type systems apply again, because we've effectively got a whole bunch of square pulses coming out, and we know that they've got a sine x over x response in the frequency domain there. And spurious phase spectrum errors because of the actual signal itself changing. It's causing effectively a phase modulation of the carrier. So whole loads of exciting stuff going on in there. So you're usually better off going for a proper D2A rather than this quick and dirty method if high fidelity is required. But if all you want to do is say modulate a lead to change its intensity, or generate a low frequency control signal, which is what you might want to do in a switching converter, then it's actually a very good solution. And it is a good solution as long as you can keep your signal at a low frequency compared with the switching frequency. But PWM as a coding solution is fine. And it also makes use of this idea that microcontrollers have hardware defined PWM as an output. So what you do is you send the information digitally to your A to D converter chip using PWM, because there's no issues with that. It's just a timing issue. So you send a pulse width modulated representation of your digital signal into your D2A converter. It then turns that into a digital word inside here, and then uses another type of D2A technique to give us an output voltage. And that actually works really well. And you can see there's a Linear Technologies 2645, which actually has 4 PW inputs. So it's only 4 wires going into this device, which allow it to output multiple analog signals. And so the number of resources required in terms of physical wires is only 1 wire per output trace. And this could be as many bits resolution in principle as the PWM can provide in terms of the accuracy of the timing. So multiple D2A channels using PWM to control it is actually a very good solution. all good. So the only other thing we need to comment on is the sigma delta converter. The sigma delta D2A converter is actually very similar to the equivalent got this all wrong, digital analog is equivalent to the analog to digital converter. So this bit is A to D, otherwise it makes no sense at all. Something is the same as itself, that's no good. So again, if you recall the idea of the sigma delta converter, we would take a sample in, we'd oversample it up to a very high frequency, low pass filter that, put it into our sigma delta modulator, and that gives us a 1-bit D2A, and then we would output that through our low pass filter. The next diagram is probably a bit easier to show what's going on. So we've got our digital word coming in, which is at Nyquist. I've got a spectrum like this if you're interested with that. We would then interpolate, or effectively low pass filter it to give us a lot more sample points in between here. So we're just filling it in. That spreads everything out a bit. We can then turn that into our modulator and do the quantization noise shaping business. We are allowed then to filter that because we haven't got all these images in there, and we get a nice smooth analog output from that. So as an example, in a CD system, the input data is 16 bits typically. Well, in all systems it's 16 bits, and is band limited to 20 kilohertz, which is the audio band. The sampling frequency needs to be at least twice this, and the standard for these is 44.1 kilohertz. We would then upsample this by a factor of 128 in a CD player, although we've only got 6 in this particular diagram or so, and that gives us a new sampling frequency of near 5.6 megahertz internally. This then goes into the sigma delta modulator, giving large amounts of noise shaping, and a 1-bit D2A is then used to output the data. And this is then filtered to give us our analog output. And the important thing is that we still need quite a good analog low pass filter at the output. The digital filter is quite tricky to make, but that's someone else's problem. And as a rule of thumb, the analog filter should have an order at least 1 higher than the noise shaping. So if you've got second order noise shaping, you want a third order analog filter to allow the noise in the higher part of the spectrum to be maintained at least a constant level. So you don't want to allow any noise back into your system, having gone to a whole load of trouble to get rid of it in the first place. So as with all these things, the higher you go in resolution and the higher the noise performance you're looking for, the more stress it puts on all parts of the system, not just the A to D. So don't make the mistake of thinking I've got a 16-bit A to D, I've got a 16-bit resolution, because you've got to have the rest of the system performing equally well in terms of the analog system and the noise levels to maintain that advantage all the way through. So just to finish off on the A to D converters, there's a nice little picture here that's showing us where the different technologies sit in terms of resolution against settling time. So that's speed of conversion, if you like. And you can see the sigma delta is very high resolution potentially, but settling time is quite slow. So high resolution, slow moving signals, and there's a trade-off all the way through between that. So you can see the types of A to D that might apply in these kind of areas. So if you want 16-bit resolution at a settling time of say 10 to 8 microseconds or so, you'd be looking at this type of technology. And if you're going for again high resolution systems, you're looking for current steering ones rather than voltage steering ones. And that is where we finish in terms of A to D converters and D2A converters. So yeah, I'm sorry we didn't finish it in the whole course, but this lecture hopefully will fill in some of the gaps. The slides will be online, and like always you just need to spend a little bit of time thinking about the concepts and getting it straight in your own mind going forward. Okay, thank you for listening.